Agriculture increasingly depends on connected control systems, but most cybersecurity tools were designed for enterprise information technology, not irrigation controllers, pumps, valves, and field sensors. We propose a senior design project with a concrete goal: build a safe agricultural honey net for AgsOC, anchored by a water and irrigation honeypot informed by the NREC N-Farms water system. It will present the kinds of interfaces and signals defenders need to understand while remaining completely separate from operational equipment. The project is core in cybersecurity operations for risk reduction in agri-networks. Students will turn expertise from UNL Matrix, UNL, NUITS, and NSRI into a working platform for research, training, and detection engineering. The need is immediate. On July 22, 2026, CISA updated a warning about attacks on internet-facing programmable logic controllers. 4 days later, more than 30 Minnesota water and wastewater utilities experienced coordinated disruptions. Reported tactics included finding exposed controllers, abusing remote access, and changing logic or configuration. Effects included pressure loss and flooding. Follow-on research still found more than 4,400 Rockwell controllers directly accessible from the internet, many through cellular routers. The lesson is simple. Attackers may not need a sophisticated zero-day. Ordinary exposure and weak access controls can be enough. AgsOC needs a safe place to observe those behaviors before they reach real infrastructure, and this project creates it. Irrigation makes cyber risk physical. A watering decision may pass through controllers, pumps, valves, pressure and flow sensors, network links, and management interfaces. If those systems are manipulated, or operators can no longer trust their readings, the consequences move beyond data. Agriculture is also time sensitive. A disruption during extreme heat or a narrow watering window cannot always wait for normal business hours. Availability, integrity, and safety become central concerns. The NREC N-Farms context gives students a clear mission and gives AgSoc a realistic way to connect cyber evidence with operational effects. Water is the first use case because it makes both the value and the risk easy to understand. A traditional SOC expects stable connectivity, standardized endpoints, centralized administration, and frequent patching. Agricultural operational technology often looks different. Remote locations, cellular links, long-lived controllers, vendor-specific tools, and tight availability constraints. The useful signals are different too. A failed login matters, but so might an unexpected mode change, a request to alter controller logic, or pressure and flow values that no longer agree. We cannot assume enterprise alerts will explain those relationships. We need an environment where students can determine which events matter, how to correlate them, and what an analyst should see without experimenting on the real N-Farms water system or any other operational asset. The mission is to build a configurable agricultural honey net with 3 personas. The first and deepest persona will resemble a plausible water and irrigation control environment informed by the N-Farms mission. It should present believable synthetic identities, services, telemetry, management pages, and operational state. It should also show an analyst how activity progresses from discovery to attempted access and control changes. The boundary is firm. The honey net must never control a real valve or pump, reuse a real credential, reveal a production configuration, or provide a path into an operational network. Its purpose is to collect defensible evidence that AgSOC can use for detection logic, response playbooks, research, and training. The first deployment is an NREC N-Farms, Informed Water Control Honeypot. Domain experts will help students identify safe abstractions. Students will build a simulation, not copy a production system. The persona can represent irrigation zones, schedules, pump and valve state, flow, pressure, alarms, and operator views. Every identifier and value must be synthetic or sanitized. The demonstration follows one clear story. A test actor discovers the controller, attempts access, and changes a simulated set point. The honeypot records the action, updates only synthetic state, correlates the resulting flow or pressure effect, alerts an AgSoc analyst, and returns to a known good baseline. Realism comes from credible behavior and relationships, not access to operational N-Farms equipment. Water and irrigation are the focus pilot, but the platform remains modular. The water persona receives the greatest depth. A connected equipment persona can present synthetic identity, diagnostics, maintenance state, and telemetry. A weather station persona can provide temperature, humidity, wind, rainfall, and pressure. Weather data can also influence the simulated irrigation state, making the personas part of one coherent environment. Sponsors should be able to deploy the water persona alone or launch all 3 as a honeynet, change their synthetic configuration, and reset them safely. Later teams could add grain systems, livestock technology, drones, or other agricultural profiles without rebuilding the core platform. The architecture takes inspiration from Teapot. Separate containerized personas feed shared collection, analysis, and administration services, We are not recreating Teapot, we are applying that pattern to a scoped agricultural platform. A consistent event schema should capture time, source, persona, service, action, outcome, and correlation identifiers. For the water persona, it should also connect security activity with simulated asset state so analysts can see both the cyber action and its operational consequence. An AgSoc dashboard will present that story, while administration services support deployment, inspection, reset, and teardown. The results should be portable and deployable without any dependency on production and farms access. Containment is part of the product. Because a honeypot invites hostile traffic, the design must assume that a persona can be compromised. The platform needs a dedicated network, explicit inbound exposure, default deny outbound access, narrowly defined administration paths, least privilege, resource limits, and reliable reset behavior. Students must demonstrate what prevents pivoting and internet scanning, how evidence is preserved, and how the environment returns to a trusted state. Farms experts may inform behaviors and scenarios, but production addresses, credentials, controller logic, and configuration artifacts never enter the honeynet. The results should be interesting to an attacker, useful to an analyst, and harmless to everything outside its containment boundary. The primary deliverable is a working NFARMS-informed water and irrigation honeypot with an end-to-end demonstration. The common platform should also support the equipment and weather personas, normalized events, correlation, and an analyst dashboard. Students must demonstrate production separation, restricted egress, service isolation, synthetic data, evidence export, and safe reset. The handoff includes source code, container definitions, tests, example configurations, operations guidance, a threat model, and known limitations. A compelling stretch goal is a cyber-physical sim, U-Law-Crew, a real working prototype in which students connect their synthetic control environment to a small physical model with pumps, valves, sensors, or visible flow. It would make the simulated consequences tangible while remaining isolated from operational infrastructure. This is a strong senior design project because it is timely, bounded, and technically substantial. Students will work across containers, APIs, state simulation, event pipelines, dashboards, testing, and documentation. They will also practice threat modeling, isolation, operational technology telemetry, evidence collection, and secure recovery. Domain experts will help them understand water and irrigation behavior without exposing a real system. The work divides naturally among persona development, containment, data engineering, dashboards, and testing, but the final result must operate as one system. The finish line is clear: one deep water scenario, two supporting personas, demonstrated containment, and an end-to-end analyst workflow. The sponsor group brings the expertise students need without taking away their ownership. UNL Matrix and AgSoc contribute security operations, detection, response, dashboards, and workforce development. UNL's Institute of Agriculture and Natural Resources, Biological Systems Engineering, and NREC contribute NFARM's context and expertise in water, irrigation, sensors, and digital agriculture. NSRI connects the project to food, agriculture, environment, and critical infrastructure security. NUITS contributes architecture, governance, and integration perspective. Students can validate requirements through scheduled reviews and possible site visits, while making their own engineering decisions in a shared repository. The result is a portable platform that sponsors can maintain and future teams can extend. Recent water utility attacks show that exposed controllers and weak access paths can produce physical disruption. Agriculture shares those technologies and adds remote locations, seasonal urgency, and direct consequences for equipment and production. We should not wait for a local incident to begin learning. This project creates a safe place to learn now. Students will build a modular AgSoc honeynet anchored by an NREC NFARMS informed water persona. It will expose realistic synthetic behavior without controlling real equipment or revealing production details. It will correlate evidence, show the attack story to analysts, and operate within a containment model designed for hostile traffic. Students gain meaningful engineering ownership, and AgSoc gains a reusable platform for detection, research, exercises, and future development. Start with water, build a capability that can grow.